I'm going to be talking with you today about a study that was completed in 2023, focused on California's controlled environment agriculture industry, also referred to as CEA. And that includes the greenhouse and indoor farm industry. This particular study took a look at HVAC, heating, ventilation, and air conditioning solutions that could save energy, natural gas in particular, in these facilities. And this was funded as part of the Gas Emerging Technologies Program. So I'm Gretchen Schimmelfennig. I'm an energy engineer at Energy Resources Integration. This project was managed by ICF, and I'm going to tell you a little bit more about the project team in just a second. So our project manager, Sharab, supported this project, and Stephen, the director of engineering at ICF, oversaw this project. I was also supported by some other team members at ERI. I managed the project along with Ethan, our engineering manager, and our principal, Eric Knoller. So today's presentation, we're going to cover the findings of the project up front, so you get some big takeaways at the top of the presentation, and then we're going to dive into the weeds, go into the CEA market in California, describe the energy consumption of HVAC systems in these buildings. If you wouldn't mind muting yourself, please. Thank you. Talk about the incumbent HVAC technologies being used in these facilities, a little bit about how greenhouse growers and indoor farmers have participated in energy efficiency programs so far, and then dive into the emerging technologies we identified, the results of our evaluation, and some conclusions and recommendations for further study. So some things to leave with if you don't remember anything else. These are the highlights of the study. So if you're not aware already, even in California, even in what might be considered a hot climate, greenhouses need a lot of heating. Energy models that we created for single layer and double layer coverings on greenhouses showcase that energy intensity for natural gas can range from around 1.7 to 3.1 therms per square foot, which means that greenhouses using single wall coverings can present a larger energy efficiency opportunity than a double layer covering greenhouse. And this is good to understand, especially as we seek to understand the overall energy use of California greenhouse stock. It really depends on the size of the greenhouse. So a therms per square foot metric is something good to have in hand. We also explored the efficiency opportunities of hydronic systems and heat distribution supporting hydronic systems, because 60 cents of every dollar spent on greenhouse heating technology is spent on unit heaters, and that's not necessarily efficient unit heaters. They're easy to buy, they're modular, they're kind of plug and play, but they aren't the most efficient heating solution. And so we find that there's a significant opportunity for introducing hydronic HVAC systems, including finned heat pipes and root zone heating systems, into greenhouses to save significant natural gas. A third major finding of the study is that really going after heating can save over half of the natural gas used in greenhouses in particular. And so we'll share with you a detailed measure table. There are 5 emerging HVAC technologies with energy benefits ranging anywhere from 6.7 to 53% annual natural gas savings. Well, what types of CEA facilities should we really target the most? We think that vegetable greenhouses present the largest savings opportunity. That represents around 20 million square feet of California farm area and 33 to 62 million annual therms of natural gas usage. And I'll tell you in more detail why we think this when I cover our annual energy usage analysis that we did for this study. The last major project finding to think about as you hear the rest of the findings of this study is that single wall coverings are predominant. These are the baselines that we see out in the greenhouse stock of California. These have low U value, but they also have pretty low light transmittance. So growers are discouraged to make a double wall covering of that material. There are, however, emerging technologies that are not yet well adopted, like double wall acrylic, that have better light transmittance and better U value that could really help the greenhouses in California currently using single wall coverings or polycarbonate coverings, which have that poor light transmittance compared to acrylic. So Heating is something I'm going to talk a lot about today, hydronic systems, as well as coverings. And so I hope that you share your questions in the chat. Let me know how you've encountered these systems in the field, maybe questions about the emerging technologies that I share to support these facilities. Before we dive into the technologies, let's talk about the California CEA market and why they use HVAC equipment. So in 2023, we estimated around 3,800 active CEA operations in California. California is a powerhouse for CEA historically from the nursery and floral markets. So California produces 20% of US nursery and floral products. And in 2017, California ranked 5th in the US for nursery, greenhouse, and floriculture product sales, going over about $2.7 billion. And I'll just note that the USDA crop census for 2022 just came out this week. So if we took a look at that data, I think that California, New York, and Florida are the three powerhouses in these areas. So California is still always going to be a very big greenhouse state and is becoming a bigger and bigger indoor farming state as well in certain crop categories. Thinking about indoor farming, you'll see on this pie chart, cannabis indoor, cannabis greenhouse as well. Those two segments of the pie make up about half of the operations in 2023. To back this up, 2022 wholesale market value of California cannabis is about $1 billion, and cannabis was California's 8th most valuable cash crop. And the last little tidbit I'll say about these crop categories is that greenhouse vegetables, even though it's a small segment of this overall active CEA operations pie chart, California has the largest greenhouse vegetable industry in the United States, and the size and market value of CEA vegetables was growing by 25% in 2017. So there's a lot of crop categories in here, but when we take a look at the area, how much square footage is being used for these different crops, floriculture and nursery farms really dominate. 46% of farm area is used for floriculture and 27% of farm area is used for nursery crops. And that's a total of almost 250 million square feet of greenhouses and indoor farms in California. If we look at this, the crops being grown indoors are mostly only mushrooms. Mushrooms can only really be grown indoors. Obviously, cannabis indoor cannabis, and then a small portion of vegetables and herbs are likely being grown indoors. But of this whole graph, the majority of this is still in greenhouse facilities. So what's the purpose of CEA HVAC systems and why are we able to save energy there? Well, growers use these systems to maintain what's called vapor pressure deficit. Vapor pressure deficit is a function of air temperature and relative humidity, and it directly impacts plants' transpiration rates, which is the plant drawing up water through its root system, up through the plant, using its nutrients, and then transpiring the water out through its leaves. Just like humans perspire, plants transpire. And so growers, as these plants are constantly pushing water into the air, growers have to maintain temperature and relative humidity to make sure the plants are growing happily and pests are not living happily. So they use equipment like shown on this slide, something like a unit heater, the one in the center left, or they might use something like the bottom right, a larger boiler system. Let's talk about the energy consumption of these systems. A big takeaway you can bring home is that natural gas for heating end uses can account for 70 to 80% of total annual energy consumption for greenhouses, and that's counting all fuels. So if you add up their gas, their electricity, and any sort of on-farm fuels like diesel or gasoline for on-farm vehicles, it's still predominantly natural gas usage that is accounting for energy use, and that's because of the need for heating. 80% of a greenhouse's heating use occurs at night. And so even in a warmer climate, when the sun goes down, they have to heat. So how does that add up in cost? Energy can account for up to 60% of greenhouse energy costs and greenhouse operating costs. So that's even including things like labor, and heating can be the second or third largest operating cost. So keep in mind that many greenhouses don't use a lot of supplemental lighting, so they might not have as high of an electricity bill as they have for a gas bill, especially because heating is something that they might have to do more often than use electricity for lighting. A note about our model that I mentioned on the takeaway slide, 1.7 to 3.1 therms per square foot, that was generated using a virtual grower model for a greenhouse in Carpinteria, California. Virtual Grower is a USDA-funded free tool that can be used to model greenhouses and is being upgraded to also model indoor farms. And the reason why we did this was that we wanted to note that facility size can really be more impactful than climate zone on natural gas consumption. And that's something I'll share with you on the next slide. We compared a lot of greenhouses in the same climate zone and found that the range of energy consumption was quite wide. But the table on the right here summarizes that when we looked at an analysis of over 90 facilities in the SoCalGas territory, and we did a weighted average of their annual therms for heating, we found that on average, CEA facilities, predominantly greenhouses, use around 120,000 therms a year. But this is, again, not on a per square foot basis. The greenhouses in this sample set could be of varying sizes. And so further study might be necessary to corroborate the modeled therms per square foot and really find out an actual therms per square foot in greenhouses in California in the field. As I mentioned, natural gas consumption for a number of CEA facilities, around 41 of them in a particular climate zone, ranged widely from as little as 100 therms per year to over 650,000 therms per year. So it could really have to do with the type of crop that they're growing, the size of the greenhouse, and how many days of the year they're operating it each year. Let's move on to HVAC technologies that are being used in greenhouses and indoor farms today. So this is a picture of a more modern boiler in a greenhouse. I already showed you a picture of the incumbent technology of unit heaters, but the upfront cost of heating systems is really the reason why growers are choosing unit heaters over hydronic systems like boilers, because capital costs for unit heaters can be 75 to 88% lower than hydronic systems. So the baseline technologies are summarized on the table on the right. I want to share that they're summarized by CEA facility type, like greenhouse and indoor, as well as technology category. So within the HVAC technology categories, there's of course heating and heat distribution, cooling, but we also included greenhouse coverings because greenhouse coverings very much influence the size of greenhouse HVAC systems. And we also included a little bit about thermal energy storage for greenhouses, as that is a practice in some larger greenhouses. So the notes on the left note that the baseline technologies for heating are going to be unit heaters, a central boiler producing steam or hot water, or potentially a combination of these systems. The age of the boiler, the efficiency of the boiler, that can vary widely. And so I'll share with you a little bit more of what we found in site visits. But unit heaters are still what we consider to be the baseline, or a boiler that's not necessarily high efficiency. Heat distribution is an interesting note for greenhouses because of the best practices that we've inherited from experts in the Netherlands. So you might see 51 millimeter steel tubing called heat pipes in greenhouses. That's something that has been brought to us by the Dutch style greenhouse construction approach. And these are often put through the canopy, under the benches, or potentially along the perimeter or above the canopy. So there's lots of ways of distributing heat in these places, but the baseline for heat distribution is bare steel heat pipes. And then on the indoor farming side, we really just want to note that there's not a lot of natural gas being used in indoor farms unless they are potentially using some sort of hydronic cooling system like a chiller. And of the facilities most likely to use a chiller, it's going to be a larger indoor farm, likely growing a high profit margin crop like cannabis or leafy greens or herbs. Before we explored the emerging technologies further, we also took a look back at the past 10 years of efficiency program participation in SoCalGas territory. We explored the types of measures that greenhouses and indoor farms had been participating in, and found that, as you take a look at the pie chart on the right, over half of the projects completed in the past 10 years were for heat curtains. Nearly 20% of them were for greenhouse infrared film, a covering measure, but for IR film, plastic film covered greenhouses. And then only a small portion, around 25% of the measures were completed for things like insulation, economizer maintenance, or boilers and water heaters. So 7%, only 7%, around 10 projects addressed process boilers or commercial hot water heaters. We also corroborated this level of adoption with Northern California program implementers. And so this finding showcases that the programs have been really getting a lot of participation on the greenhouse coverings side of things with curtains and film, but the heating equipment itself, like the boilers, is not something that's been addressed fully yet. So this is an opportunity for this study to address. The emerging technologies that we looked into include gas consuming appliances, heat distribution, and greenhouse coverings. And we looked into 5 of these technologies. The table on the right dives into these 5 technologies and describes the emerging technology on the left, the baseline technology in the middle column, and the natural gas savings potential on the right. And so I'll go line by line. So low mass boilers. Low mass boilers are a high performance boiler that can heat up a lesser amount of water, a lower mass of water than a traditional boiler, and can also achieve higher efficiencies. And so we have seen models as well as manufacturer case studies demonstrating 36 to 38% savings compared to a baseline of unit heaters, and find that this could be a measure that can be supported by 2 other heat distribution measures, including finned heat pipes and root zone heating. We found that bare steel heat pipes have not been really comprehensively compared to heat pipes that increase heat transfer via different types of material instead of steel, or different types of molds instead of just a bare steel heat pipe, perhaps something with crenellations or higher surface area. And so a manufacturer has demonstrated savings of 6 to 11% compared to a bare steel heat pipe, but we find that there could be even additional savings because there's not yet much study there. And this is because 5 to 10 times heat output with 80% less water should result in increased gas savings. I'll just note that the manufacturer was comparing their generation 1 finned heat pipe to their most recent generation of finned heat pipe. There's actually not a study comparing bare steel heat pipes to finned heat pipes. This should be a conservative energy savings estimate. Root zone heating. It's been around for a while, but is not widely adopted. Many growers choose to heat the greenhouse. They heat the space. They don't heat the plants. So a great efficiency measure would be to heat the plants directly and reduce space temperatures of the greenhouse. So the unit heaters and the boilers are not running as often, or they're not running to as high of a temperature. And so heating can be distributed on top, above the canopy, or along the sides of the greenhouse. And instead of doing that, moving the heating distribution to mats with hydronic piping so that the benches are heated directly under the plants, or other sorts of perhaps underbench finned heat pipes, that can result in 19 to 53% annual energy savings when compared to top or perimeter heating. The 4th row here is about indoor farms. The opportunity for replacing an electric chiller in an indoor farm with a new type of hybrid gas electric chiller is an opportunity that we found. Like I mentioned, the only farms really using a lot of indoor farms using a lot of natural gas are larger indoor farms using hydronic cooling, and most of them are using electric chillers. And so we found that there's a new product that allows the facility to use both gas and electricity for chilling, and the equipment itself is given information about the cost of electricity as well as the carbon emissions of the grid at any particular time, and it can choose to use gas or electricity depending on cost savings or emissions savings. And so we found that initial studies show 30 to 60% lower total energy costs and carbon emissions. And this could be most effective for growers with high electricity rates, which would encourage them to use the gas side of the chiller. And also growers with perhaps dirtier grids could also be a good opportunity there. The 5th measure that we explored is greenhouse coverings, and that is, like I mentioned, encouraging growers to use a double wall covering that still has good light transmission compared to polycarbonate. So 25 to 47% energy savings have been shown with a double wall acrylic covering compared to a single layer polycarbonate covering. So a little tidbit about root zone heating. One thing to note is that root zone heating can only satisfy a portion of the greenhouse heating demand, but you can reduce air temperature set points by 5 to 10 degrees Fahrenheit. So we evaluated these 5 technologies through, as well as the baseline technologies, through a number of mechanisms. We executed surveys in May through August, as well as interviews and site visits. And like I mentioned, we did some energy data analysis of over 90 facilities served by SoCalGas. So let's talk about the survey participants. The typical respondent to the survey was a greenhouse grower cultivating vegetables. We actually were able to reach growers of all different types of crops, which represents pretty well the square footage demographics of the California greenhouse industry. Not a ton of respondents from the cannabis industry, but that's not terribly surprising as they're generally harder to reach and harder to get to respond. But given the predominance of the ornamental and nursery crop market in California and the greenhouse market in California, we had those types of growers really respond to the survey. We found that in the survey, growers are using boilers in about 45% of the responding facilities, but that many of them are using older boilers. So over a third of greenhouses are using boilers that were installed prior to 2010. And I'll share with you in our site visits that we also found some boilers in site visits that were quite a bit older. So there could be great opportunity for that low mass boiler measure that I mentioned earlier. On the greenhouse covering side, I think this is an important finding that's relevant also to those of you who may work in the California Energy Code space. There's a new California Energy Code requirement mandating that growers use 2-layer coverings if they are building new greenhouses or doing major renovations. It does not apply to replacements of existing 1-layer coverings, but it is good to note that out there in the market, there are already growers using multiple layers, but that overall a little less than a third of our respondents use single wall coverings, and those are growers that could benefit from an efficiency program helping them upgrade to a 2-layer covering. We interviewed a number of stakeholders to understand how these technologies are emerging in the market and how utilities might be able to support growers adopting them. And we were able to reach a great number of manufacturers. That was kind of the typical respondent to our interviews, but we also interviewed consultants in the CEA industry, academic researchers, industry associations, and energy efficiency program implementers. And so I'll, like that initial findings slide, I'm going to roll through these findings so that you can think of some takeaways from these interviews. So the first takeaway from our interviews was that low mass boilers have very low adoption so far. They have significantly higher capital costs than unit heaters. And we can really demonstrate through our interviews that these are adopted in less than 5% of California greenhouses. We note that unit heaters are most commonly used by standalone or small single span greenhouses, and that those types of greenhouses might be harder to get boiler technology to be adopted within. We talked with some academics as well as design and construction professionals about root zone heating, and I really liked this quote. It's called the Cadillac of heating systems. It does have a cost that depends heavily on how much of that heat load is going to be covered. Is it going to be 30% of the heat load or 40% of the heat load, for example? We found that in our interviews that less than 10% of greenhouses industry-wide have applied root zone heating across all cultivation spaces. And when I say industry-wide, I mean California industry-wide. On the finned heat pipe side, again, very low adoption rate. Inside the California greenhouse grower segment that uses hydronic heating systems, only 2 to 3% of those apply finned heat pipes for heat distribution. Bare steel heat pipe is the standard practice, especially due to the popularity of Dutch style greenhouse design. And if it's not a Dutch style greenhouse, they're probably using a unit heater. So this is a great opportunity to find ways to get growers to adopt hydronic systems, as well as adopt finned heat pipes and root zone heating at the same time, perhaps a combination of one, two, or all three of these measures. The greenhouse coverings measure, when we talked with interviewees about this, it's really a hodgepodge in California, even at the same facility. So determining a baseline was difficult, but we did settle on single layer polycarbonate panels as the baseline. Plastic film greenhouses kind of have their own baseline, and glass greenhouses are around, but may not be the baseline for California. So that is why we chose single layer polycarbonate, despite there being a mix out there. The most common is polycarbonate, though if you're dealing with a Dutch style greenhouse, the glass is most likely the baseline. I mentioned Title 24 briefly in a slide or two before this, but just wanted to reiterate it here. We talked with one of the policy makers involved in supporting the code changes, both in 2022 and 2025, and they confirmed with us that replacements of existing coverings do not trigger California Energy Code. And if it's not a conditioned greenhouse, it also does not trigger energy code. So understanding how conditioned a greenhouse is may make that code not apply. So we still find that a measure supporting double layer greenhouse coverings is possible because replacements do not trigger code. On the indoor farms note, chillers, we talked with folks working on indoor farms for cannabis and food, and they noted that 20 to 30% of indoor facilities are using chilled water systems, and that they're most cost effective for buildings larger than 100,000 square feet. We visited 5 sites for this study, and the typical CEA site that we visited is an orchid greenhouse in California Climate Zone 6. We visited sites all across the California climate zones, including 3 different climate zones, and covered 4 different crops. The typical site was a greenhouse, but we did visit 1 indoor farm. The site visit summary table is on the right. And it showcases that we were able to visit all of the major categories of crops represented in the California CEA market. And a couple of things to note is that the average greenhouse facility that we visited was around 375,000 square feet. It's good to note that greenhouses are usually measured in acres, not in square feet. So this is not even the largest type of greenhouse that you might see in California. And then the indoor facility that we visited is much smaller and had around 31,000 square feet of cultivation space. That was a cannabis grow. So if you take a look at the table, like I mentioned, we were able to visit a variety of climate zones, and you can see from the greenhouse covering type column that we saw a variety of coverings as well. 2 of the greenhouses used single wall polycarbonate, 1 used double wall polycarbonate with a seasonally applied whitewash, and the 4th greenhouse used glass with seasonally applied whitewash. The heating systems at the greenhouses are actually demonstrating more of the kind of middle of the road efficiency wise. We didn't actually observe any greenhouses using unit heaters, but that may have to do with the fact that we were visiting larger greenhouses with larger commercial distribution, well established, some of them decades long, having been in California. So in some ways, these types of facilities are more likely to be using boilers, but this is just a sample, and we found that of the boilers we saw, 1 of the facilities used a steam boiler. And in the indoor facility, on the gas side, the only place that gas is really used in the facility is on the hot gas bypass for their HVAC system. Back to the greenhouses, on heat pipe type, you can see that we visited a lot of Dutch style greenhouses. They already use underbench heating, but they're using bare heat pipe. Some of them had a little bit of above canopy heating distribution as well as underbench. And then on the cooling side, you can see that, greenhouses don't really use gas for cooling. They're mostly using natural ventilation through vents and fans. One of them used an evaporative pad and fan cooling system, which is not going to use gas, but is using a lot of water. And then on the indoor facility side, you can see that the cooling system is using a dedicated outdoor air system with some energy recovery and an integrated cooling and dehumidification system. So not a lot of gas use on that particular facility. But we learned a lot about the baselines in the greenhouses and learned about whether our emerging technologies have the benefits that we thought they would. And so this is the summary of what we found and pictures of everything that I have described so far. So again, I'll run through the table starting at the top, low mass boilers. That picture is on the top left, and this replaces unit heaters with high efficiency boilers. The second measure we proposed is finned heat pipes, which replaces bare steel heat pipes with aluminum radiant heat distribution with high surface area to enhance heat transfer. That's the picture on the top right. The middle row, root zone heating with reduced air temperatures, you can see a picture of that on the middle left. There are no plants on that bench, but you can see all of those capillary tubes. That's where the hot water goes through and delivers the hot water directly to heat the plants rather than heating the air around it. And so that would replace a perimeter heating system or a unit heater system with root zone heating, and would result in energy savings from reduced space temperature set points as well. The indoor hybrid gas electric chiller option is showcased in the picture in the bottom right, and that would replace an all electric chiller, which would enable there to be gas savings as well as emission savings from perhaps expensive electric grids or electric grids with high emissions content. And the final picture in the final row, bottom left picture, shows a double layer acrylic greenhouse covering, and that would replace a single wall polycarbonate or glass covering and provide substantial energy savings. And I'll sit on this slide for a little bit to let you look through it. These emerging technology studies require that we investigate all the different types of benefits and costs to the measure. And so the rows of this table showcase the type of measure application that we might choose for this project, the building type, as well as the measure costs, annual natural gas savings, associated greenhouse gas savings with the energy savings, the associated cost savings for the energy savings, the improved efficiency over the baseline, the simple payback, the expected useful life, and our proposed incentive approach. And so you can see from the 5 measures that we explored, the greenhouse measures, the one with the lowest, i.e. the fastest simple payback period, is identified as the double wall acrylic measure. And then following behind that, the low mass boilers measure. And then after that, the root zone heating measure. So these show good potential. And as you can see, also offer some substantial energy savings. So in the natural gas savings row, you can see that the double wall acrylic savings is described in therms per square foot. So if we think back to that range of annual natural gas usage for a greenhouse of around 1.7 to 3.1 therms per square foot, you can see that we're estimating that a double wall acrylic could save a substantial amount of that annual natural gas usage. And then the other heating measures offer, anywhere from 13,000 to over 60,000 therms saved every year. Along with these energy benefits and financial benefits, there are other non-energy benefits of these technologies, and each of these technologies provides a technical improvement. Something special to note about CEA businesses is that their non-energy benefits include the impacts on plants, which are living things that have an impact on the final product that the business sells. But there are so many qualities to plant production that may not be familiar to you that it's really important to think about when documenting the benefits of these projects. So some examples could include cycle time. How long does it take to go from seed to harvest? Am I able to improve the lettuce growing cycle from 5 weeks to 4 weeks so that I can grow a whole another harvest of lettuce every year? Is there a quality characteristic that is changed by this measure? Am I able to perhaps grow CRISPR lettuce or grow a type of lettuce that is tastier or has different nutritional content. These are real things that are impacted by systems such as horticultural lighting, as well as environmental control. There are academics that have studied the impact of temperature control on different types of crops, and these sorts of studies continue. And the last non-energy benefit that is good to look into is yields. Do you, with this technology, impact the total production of this farm, which may be making money based off of the pounds that it sells? So with certain crops like cannabis, this is very important. With other crops like floriculture, it may be less important because they sell based off of the pot, not the amount of flowers in the pot. So these are really interesting qualities to look into. And the table on the right summarizes the quantitative and qualitative sort of improvements that you see, the quantitative improvements to the qualities that you can see in CEA facilities. So low mass boilers, while they offer higher combustion efficiency, they also can reduce the amount of water used for heating in these facilities. Finned heat pipes, while they improve heat transfer with better thermal conductivity, they also don't have to be painted like heat pipes have to be. Root zone heating, while it delivers heat better to plants, it also can speed up production time and impact those quality characteristics that I mentioned earlier. Hybrid gas electric chillers have those lower energy costs, and potentially, if a grower cares about the carbon emissions, that could be a business benefit to them that matters, reducing carbon emissions. And then on the greenhouse covering side, double wall acrylic panels, while they save energy from reducing heat loss, they also offer higher light transmissivity, which can translate to production benefits for plants as well. Some findings that we found regarding barriers to efficiency that I think are important to share are that, no surprise, capital costs are the biggest barrier to energy efficiency implementation for CEA businesses. But it was interesting to me to see that labor cost for installation is actually of greater concern than material costs for respondents when we asked them last year, and that only 12% of growers are actually concerned about system performance. It seems like they can actually trust most energy efficiency projects, or most growers can trust energy efficient products. However, 12% is still a significant portion that should be addressed, and there's an opportunity to build trust there and persuade skeptics with education and other sorts of awareness campaigns so that growers can understand why these projects are of benefit to them. Another interesting finding is the desired payback period for a typical grower. We found that growers, and this is not surprising in certain crop categories like cannabis, many growers really need super fast payback periods because they aren't able to access a lot of financing and loans in the ways other types of growers are. But regardless of crop type, we found that more than half of growers need payback periods to be less than 2 years, which for some types of businesses is a pretty short payback period. A third of growers can implement projects with a 2 to 5 year payback period, but basically no grower is able to stomach a 5 to 10 year payback period. And it's important to note that smaller growers, smaller CEA operations, hard to reach customers in disadvantaged communities, they might not be able to adopt CEA HVAC measures, which have long payback periods due to the need for their business to stay profitable and not take on a large amount of debt or hold on to money for a large capital project. We suggested the following incentive approaches for these measures to SoCalGas. We find that 4 of these measures are novel, while 1 of these measures is an improvement to an existing measure. And I'll go through the table as I have done so far. The low mass boiler measure is suggested to be a deemed measure, as it is an update to an existing boiler measure that is offered to agricultural customers. However, it's not really customized well for greenhouses. And so this could be an update that incentivizes them better and should increase the adoption rate of low mass boilers. We see that there are 2 other measures, finned heat pipes and double wall acrylic panels, that can go in a deemed approach if data from field testing and pilot projects can support energy modeling for each California climate zone. So finned heat pipes, heat transfer improvement is consistent and it can be modeled, but we really need to make sure we can model it for every climate zone. And then greenhouse coverings. I'll get to that one in a second, but similarly also would need to be modeled. Root zone heating is proposed as a custom measure, as energy inputs for energy modeling vary greatly by facility type and behavior. So the proportion of the heat load that's going to be served by the root zone heating system can be varied. The space temperature set point adjustment can also vary. And so those would be inputs to an energy model that would probably need to be used for a custom measure for some time. And then the second custom proposal that we offered was the hybrid gas electric chiller, especially because it's a dual fuel equipment that can use gas and electricity based off of the inputs. It's definitely something that would need to be custom, at least to start. And to finish off the double wall acrylic panel measure, we suggested that it could go deemed as it could be modeled consistently for California climate zones based off of the U value improvement. Our conclusions and recommendations are that these 5 measures should be developed into measure packages. And we are going to have this full study published on the ETCC website so that you can review all of these things I said in greater detail. And I want to share also that we explored 4 other technologies, but found that they are promising and commercially available, but that follow-up field or lab testing is recommended. This includes low emissivity anti-reflective glass, double wall insulated glass panels for greenhouses, ETFE film, which is a special type of film covering for greenhouses, as well as phase change material for thermal energy storage for greenhouses. These are promising, but not ones that we recommended in the final study. And we're excited to share that future study is being explored to determine the best pathway for high priority technologies. And that could include collection of data from on-site pilot installations of high priority measures to support measure package development. We also thought that climate control technology with energy monitoring could be leveraged, and that this future study could investigate gas usage by square footage and by climate zone. So as we plan this phase 2 study, the goal is to support utility measure package development and the creation of new natural gas efficiency measures, identify barriers, and come up with intervention strategies. And the end state is to integrate, hopefully, some cost-effective gas efficiency measures into the CEA sector. And I look forward to your questions. Thank you very much for your attention.
Great, Gretchen, thank you. We have a couple of questions in the chat if you can see. If not, I can feed them to you, but I was just wondering if we can just go down the line, starting with Alex's couple of questions and answer the rest.
Sure, sounds good. I'm going to read the question out as well for the recording. Is the higher capital cost for adoption of low mass boilers instead of unit heaters the mechanical units themselves and all the piping that's needed? I'll answer that. Yes, the low mass boiler is priced on the square footage, including the distribution equipment for a new build. But if you are dealing with a a retrofit project, the higher cost of a low mass boiler compared to a unit heater would likely be smaller if they didn't need to do a large amount of infrastructure improvements. I would say that overall, the 75 to 88% higher cost that I quoted in this presentation is based off of the boiler alone, though. So this is something to consider. Can low mass boilers do space heating? Yeah, that's the idea, that they can serve space heating needs and water heating needs depending on what you're looking for and how you're going to distribute the heat. A low mass boiler can do space heating by going to a finned heat pipe or by going to a bare steel heat pipe. It really depends on what the greenhouse is choosing to do. Are you talking about space heating for humans? Yes, the boiler can also provide finned radiant heat to spaces that are also housing humans inside the greenhouse. The question about Title 24, when it says a conditioned greenhouse, is this for cooling or heating or both? It's for both. They have a BTU per square foot limit for cooling and a BTU per square foot limit for heating. And if you surpass either of those, you're considered a conditioned greenhouse and the code applies to you. And you need to try and See if your project triggers code due to it being a major renovation or it being new construction. What is the typical percentage of total operating costs in a greenhouse for their energy? I'll actually go back to that slide. It's basically around 60% of total operating costs can be for energy, and for natural gas in particular. So I'm sorry, it's a little bit further back. Here we go. Right here we go. So energy accounts for up to 60% of greenhouse operating costs. And that's for natural gas. So if we look at their operating costs, heating for natural gas can be second or third. If I go back to this slide as well, if you look at total energy consumption, including natural gas, electricity, and all other on-farm fuels like diesel or gas, we're looking at 70 to 80% of the total consumption. Okay, I think I just addressed that. The next question is, how do the more efficient technologies speed up the yield time or produce more yield, produce more product? It's a great question. So I'll go back to the non-energy benefits slide. So if you take a look at academic researchers, they have compared the plant outcomes for a particular temperature and relative humidity set point to another plant outcome with a different temperature and relative humidity set point. So in some cases, they've studied the benefits of consistent set points, i.e. well-maintained environmental conditions, or they have taken a look at like maybe a facility that's constantly having temperature deviations because they're not able to maintain microclimates in the greenhouse. And those studies have found that the crops are able to produce more flowers or produce more fruits or produce more leaves, if we're talking about a leafy green, because the plant is not as stressed out. In some cases, we want a plant to be a little stressed to maybe get it to produce extra flowers or maybe have a more dazzling color like a purple lettuce. But in general, a consistently maintained environmental climate is going to produce a plant that's happier and is going to be more productive. There are studies that show that plants have to kind of choose whether they're going to use their energy for morphology or for production. And so, for example, if a plant is not getting its preferred environment, it might spend energy on hardening up its stems, or it might spend energy on stretching itself out instead of spending time on the thing that you're actually paying money for, the leaf of the lettuce or the fruit of the tomato. I hope that helped. I highly recommend checking out the literature on this, as I'm not a plant scientist. I'm also not an expert horticulturalist, but a lot of those folks have been publishing on this topic for some time. And there are some manufacturer case studies with growers on the cannabis side, on the food side, on the floriculture side, where they describe the benefits to their crops. And then the second part of that question was, does this mean growers need to modify heating schedules or keep the same schedules with the new tech? It's up to them. As they deal with new tech, they might find that they can change their set points. For example, if they're implementing root zone heating, they might find that they can definitely change their space temperature set points or tweak and peak the set point that's going to the root zone mat. They might not need to change schedules at all. They just might find that they don't see their equipment running as often. Can low mass boilers be used to replace larger existing boiler systems in modular setups? Yes. The idea would be that growers could phase out replacements of their boilers over time, integrating low mass boilers in their place. How long have they been using low mass boilers? Anecdotally shared in the comments, low mass boilers can have a higher failure rate. I can't say that I've seen evidence that low mass boilers can have a higher failure rate in our literature review and work with our manufacturer partners and in-site visits, but that's something that I'm excited to explore perhaps more with phase 2 study. I think that low mass boilers have been in use in other countries for a longer time and have been demonstrated in countries for more than 10 years. So I think that I'd be interested to learn more about the failure rate documentation. older boilers also have high failure rates. So I am curious if there's any other questions from the chat, or if anyone wants to raise their hand and unmute themselves.
I think we got another one from Crystal from Linkus.
Thank you. Are there any additional design considerations with the low mass boilers or finned heat pipes? Absolutely. I think that something to think about with low mass boiler design is how the boiler system is going to serve the different process activities happening in the greenhouse. And one of the things that I've heard quoted from experts in the greenhouse is that in the greenhouse space is that when you've seen one greenhouse, you've seen one greenhouse. So in my experience with the low mass boiler designs is that it's very important for these to be customized to each facility. An understanding of the amount of water being used for things like irrigation and fertigation might need to be understood if the grower wants to use the boiler system to temper their water. That's something that I've seen in my area in Vermont. It may not be as common or necessary in California, but I guess the general message is that the design considerations for low mass boilers and for finned heat pipes is that these are custom process equipment system designs that are going to incorporate a lot of owner's project requirements and are going to require system details and diagrams that should be thoroughly explored by potentially third-party consultants, commissioning agents. But overall, low mass boilers have the potential to save a lot of energy over unit heaters and have been demonstrated in the industry for some time. They're just not highly adopted in California yet. On the finned heat pipe side, I would say similarly that they are going to need to have customized designs based off of the crop type, height from bench, as well as potentially how much water you're going to need to push through them to achieve the set points that you desire. Any other questions? These are great. Keep them coming if you have any others. I'll put the contact information slide back up. So if you want to reach out, we're interested in hearing from you, especially if you have thoughts about contributing to the phase 2 study. And I'll also go back to the ETCC website page. So this is where the study will be posted, etcc-ca.com. If you search greenhouse HVAC in the search bar, you'll also be able to find it if you don't remember to click this link.
Hey, Kate, this is Crystal with Linkus. You mentioned the recording is going to be available, but not on the website. Are you emailing that, or is that somewhere else?
Yeah, so I'll be distributing them by end of today, maybe tomorrow, for the recording, which will link to our YouTube, and then I can also link the slide. Yeah, it's we have a YouTube account. So yes, it will be on our YouTube, and then I'll also distribute the slides. So Gretchen, this link will be in the slide deck, as well as the contact information for anyone who wants to reach out. But yeah, everyone who registered and attended today will get those slides and recording.
Thanks.
Any other questions?
Thank you, Gretchen. Great presentation.
Thanks. I'll let Kate close it out then.
Yeah, thank you so much, Gretchen. All right, I'll end it here, and we'll hope to see you guys at the next webinar. If you have got an invitation to this one, we'll be sure to get you on the list for the next one, and feel free to pass it along. Thank you so much, everybody.
Yeah, thank you, Gretchen. Thank you all for attending.
Thanks so much.
Thank you all for
Presentation.
Thanks, everybody.
Thank you.